Welcome to section 10.4, the very last section of notes for Math 141. This is over hypothesis testing when your sample sizes are small. So we've sort of waved our hands at this before. What do we do if our sample sizes are technically too small? We've had this happen to us when we were doing some stuff in chapter 11 and we just said, hey, we'll assume everything's okay and continue. But we actually have a specific thing that we can do here in chapter 10 with these categorical variables. So we want to look at what we can do. There's actually two different approaches for dealing with your data if you have expected counts less than 5. So you can either combine categories up, just make less but larger categories to bring those expected values up a little bit, or you can use what we call Fisher's exact test, or what exists as Fisher's exact test. So first we're going to look at combining categories. And the first example we're going to do there is a revisit to something we talked about earlier, which was the swine flu pandemic and how we found that actually occurred less frequently in older people because of immunity they had gained during prior flu seasons. Well, now we want to look at the rates of hospitalization for swine flu in the different age categories. So if we find different hospitalization rates, what that might suggest is that the severity of the flu is different by age group. So maybe it might be that older people are less likely to get it, but if they do get swine flu, then maybe they get a more severe form of it, or, once they do contract it, it's a lot worse for them and they end up being hospitalized more. So we are going to test the hypothesis that hospitalization for swine flu is associated with age using a significance level of 0.05. So let's go ahead and write our null, and it's almost written for us right there, but we are going to test that hospitalization for swine flu and age group. And again, we assume they are not associated. And another way to say that is that they are independent. And we are trying to show that these things are associated. Okay, so we've got the following table showing the observed and expected counts in the 6 different age groups that were created by the medical professionals. And it noted here that several of the expected counts are below 5, and those have been flagged here in red. And you get the benefit of actually seeing this on my screen in color. And they even have a warning down here. Now, this is not a StatCrunch output, but StatCrunch will warn you if any of your expected counts are below 5. So it says at least one of these is less than, and this one says less than 1, but so that's even worse, but they're definitely less than 5. And it even warns you here that the chi-squared approximation is probably invalid. Okay, so what's one thing that we can do? We could just combine these up into different categories. So what if we just took everyone under the age of 15 and made this one category? And then we left, this was a pretty big category, maybe we leave that one alone. That one wasn't a problem. And then what if we lump everyone over here together and just make 3 very big categories? Well, if I take that up, now what I need to do is I need to just add all the different values. So like I can add these up and say that there are 16 observed in this box now. And if I add those values up, my new expected is 14.41. And I can do this all the way across. This one's going to be the same. This one, if I add everything up, I'll get 10 observed. And if I add 3.84, 2.04, and 0.57, I get 6.45. Total. The totals will still be the same, so I can just put these in. Now the bottom totals may not be, because this is how we're combining. So now I need to add these together. That's 239 And adding the expected values together gives me 240.59. This one we're not doing anything with since it was already big enough. And on this last one, the 30 plus category would be 104 with 107.55 expected. Then I have to add the totals down here as well. So this one stays as, this middle one stays as 250. Then I would have 255 and 114. Okay, so all I did was take some time to combine these very small categories up into slightly larger categories, and I noticed that I fixed my problem now because the smallest expected count is now just barely over 5. So we're good at this point. Now we can go ahead and run our chi-squared test. So now we can enter this data into StatCrunch and find the chi-squared statistic and the p-value. So I'm going to just open up a new StatCrunch, and I've already put this in. What I want to make also an important note about is that when you're doing your chi-squared test for independence, you only put in the observed values and you do not put any totals in. So I'm going to go back to this chart, and I'm going to use a red pen. Notice all I'm putting in is this part, so I'd use the observed values only and no totals in StatCrunch. So all I'm going to put in are these numbers, only what was observed. And I have already done that, so I have my under 15, and I didn't leave myself room, so I guess I'll do it over here on the right side. This was a yes for being hospitalized, this was a no. So I can put that on either side because I forgot it. So now I'm going to run my test. So when I'm running my test for independence, I have to go under Stat, Tables, Contingency, with Summary. Which columns am I using? I'm using those 3 kind of categories. And I had to choose, I have to put something as my label. So that's why I went ahead and put something over there in variable 4. I needed to put something somewhere because it will yell at you if you say nothing there. So tell it something. I could choose if I wanted to display the expected counts. I should get exactly what I've already calculated, but if I wanted to double check it, I could. And again, this is defaulted on the test for independence, so I don't need to change anything else. Okay, so I can check all my expected counts in parentheses. They all look the same as what I've calculated already. So I can record now my value, my chi-squared value, and my p-value. Come back over here and switch back to my blue pen. My chi-squared value was about 4.23, and the p-value was 0.1201. So I can interpret that now. I can say since p came back larger than 0.05, we're going to fail to reject the null. So we've failed to reject, go back up and remind ourselves, we've failed to reject this, which means we're keeping it. So we have decided that actually hospitalization for swine flu and the age group you're in do not seem to be associated. Or another way to say that is to say that those two things are independent. Now, what's important to kind of note here is there was limited data provided. So based on this limited data, we do not have any information to show that those two things are associated or not. It's kind of a conundrum because it's like I would like more data to make a better decision, but more data would mean that more people would have to have the swine flu. So we don't really want more data. And that's a lot of times the situation that you find yourself in. Okay, so the advantage of combining columns, like the advantage of this strategy is that you can proceed and you can use that chi-squared test that otherwise would give you inaccurate p-values and possibly lead to wrong conclusions. However, there are also some disadvantages of combining columns. First of all, sometimes if you combine your categories, you lose a lot of knowledge, right? We lumped everyone who was 30 years and over into the same category. And there's a lot of difference between a 30-year-old and a 90-year-old as far as whether you think that that person maybe would be hospitalized with the swine flu or not. Same thing, everyone from 14 years old to a newborn baby were lumped into the same category. So we've lost a lot of information, and it kind of makes your results a little inaccurate in and of itself in that way. And also important to note is that the chi-squared test is an approximate test. You'll hear it referred to, it's an approximation. It gives you an approximate p-value. So that usually doesn't pose any problems. Approximation is good enough as long as you have a large sample. But if you're in the situation where you're changing your groups to try to get your sample sizes to be big enough, then you probably have pretty large samples. And in that case, the idea that the chi-squared is an approximation can be off enough that it causes troubles then. So this is like combining categories is one way to get through it, but there is another way that is much more reliable, and we're going to talk about that next.